Preparation of B2H6. First method. First you take BF3 and then take it in NaH. In this, Na, this will be plus, this will be minus. In B, this will have plus 3 and this will have minus 1. This plus and F will form compound and B and H will form the compound. If we take 2 moles of BF3, you will find 2 moles of BH3 plus this and 6 moles of NaF. That is basically B2H6. Then BF3 with LiAlH4. We know LiH4 is LiH plus AlH3. So if we write that, in this Li will react with F and H will react with boron, and this F will also react with this. And if we need 2 moles of this, so we will basically get BH3 plus LiF plus AlF3. If we take so basically when we so will be 4 and 4. And now third one will be I2 with NaBH4, and this we know is NaH plus BH3. Now if we need 2 moles here, so we need 2 here, we need 2, we will have to take 2 also here. And with this we know this is plus and this is minus. 1 mole of Na plus will react with 1 I, and 1 mole of this will react with another I, and they form NaI plus HI plus, and this 2BH3 will stay as it is. And that will basically form B2H6. And we know that 1 more NaI is still left. So if we react this here, we know this is plus and this is minus. Na plus will react here with the I minus, and this will react with here NaH will be there. This will react with H, this will, so you will get 2 NaI plus B2H6 plus H2 gas. So this is the gas that is released. Then we have B2O3 in the presence of aluminium plus H2. We know this in itself will form AlH3 in the presence of heat, and AlH3 plus B2O3 will basically form B2H6 plus Al2O3. Now reaction of B2H6. Now if we take 2BH3, that is basically B2H6, in oxygen, we get B2O3 plus H2. It's basically like, it's combustion, right? How you take CH4 plus O2 gives rise to CO2 plus H2, same thing. Then we have BH3 with H2. We know that this gives H3BO3. If you see a B plus 3, and this will become OH minus and H plus. So this OH minus will attack here and HH will form, and this will release H2 gas. Then we have nucleophilic attack on B. Okay, the first one is symmetrical cleavage. Now basically we have here it's 120 degrees, here it's 97 degrees. In symmetrical cleavage, you have it going like this. And basically in this reaction, what happens is that you have NR3 and NR3, so you have a lone pair on nitrogen each, and one of this lone pair goes to this boron and another pair goes to this boron, so they both are equally getting, and you will basically get 2 moles of listen here, HHH. This is how it happens, and the R can be anything like CH3, C2H5, and anything. And one more that you should remember in this example is B2H6 with 2CO gives rise to two BH3 and coordinate bond CO. So basically here C has a lone pair, so that's the point here. So that lone pair goes to B and you get 2 molecules. This is symmetrical cleavage. And then we have unsymmetrical cleavage, and here you basically have yeah, it's like one boron has only 2H and the other has 4. You're cutting it here. This basically results in BH2 positive and BH4 negative. So this is how the compound is. And now when you have here you have NH3 and NH3, and you have lone pair here. The thing here is both the lone pairs go to the same boron, that is okay, to the same boron. So now it's basically BH2 NH3 taken twice positive and BH4 negative. And this is also same for B2H6 in the presence of RNH2, that is BH2 RNH2 taken twice positive, BH4 negative. And the same thing for B2H6. This is first of all 1 degree amine, and then you have R2NH, and this is 2 degree amine, and that is BH2 NHR2 taken twice and plus BH4 minus. So even in these, except for R3 and the 3 degree amine, here you have symmetrical cleavage. The most easiest. Okay, then you have methylation of B2H6. And this is the basically only the terminal here you see only these 4 terminal carbons will be substituted by the methyl group. So you have CH3Cl plus B2H6 . One second. This will basically give BH2 and CH3 taken 4 times plus here if you're having the 4, this will be reacting with the 4HCl. I got it here, I'll just draw here. This will be like this will be the compound here. This is your normal B2H6 diborane. Now the most important, not the most, I don't know what B2H6 reacts with NH3 at low temperature. It gives B2H6 dot 2NH3, and this is basically what we saw just now, that is B2NH3 taken twice, sorry, BH2 NH3 taken twice, whole power plus, and BH4 minus. This is at low temperature. And when this reacts with NH3 at 200 degrees Celsius, it gives B3N3H6, which is inorganic benzene. And when B2H6 reacts with excess NH3 at more than 200 degrees Celsius, it becomes Bn to the power n, and that is basically polymer of boron nitride or inorganic graphite. And one thing you should remember is that as temperature increases, number of hydrogens decreases. Like here you have 6, 7, 8, 12 hydrogens, and here you're having 6, like 12, 6, 0. Temperature is increasing, number of hydrogens is decreasing. Now about that's inorganic graphite. This is basically Bn to the power n. It can be lakhs, whatever. So we know that graphite graphite literally looks like and then you have double bonds here, so that's how graphite is. Inorganic graphite is the same. You have B, and you have double bond, and in this you see B is having sp2 hybridization and N is having sp2 hybridization. No, inorganic benzene, which is also known as borazine and borazole. So this is basically B3N3H6. It looks like and we know nitrogen has lone pair, so it gives to this gives to this, and this gives to this. And we of course have hydrogen. So in this nitrogen, both B has sp2 hybridization and N has sp2 hybridization. In this boron is electron rich. Sorry, nitrogen is electron rich. Yeah. Okay. And boron is electron deficient. And hence we see back bonding. So, and hence we see this back bonding in here. Now, some parallels between benzene and borazine is that benzene and borazine are both isostructural, that is, both are planar molecules, both are planar sp2 hybridization and all. Isoelectronic, both have 42 electrons. Non-polar, that is net dipole moment is 0, and both are aromatic. And we know some properties for aromaticity is having 6 pi electrons, planar structure, showing resonance. But one thing where they both differ is that borazine is more reactive than benzene. And this is because here in benzene, you see here you have carbon, so there's no net dipole moment in the bonds. So there's no dipole moment in the bonds. Here you have the dipole moment. So nitrogen is more electronegative than boron, so you have dipole moment here. Hence this is more reactive than benzene. Let's take hydrolysis. Of B3N3H6, and this will basically give us Here when you adding water, this we know it's H plus and OH minus. So when the bond is breaking between them, you get this will become negative and this will become positive. So this will take OH and this will take H. And same thing here, this will take H and this will take OH. We also know that there is a bond breaking here in boron. Here you have this is plus, so here you get OH and this is H. So basically what you get is 1 N with H, that is NH3, which is ammonia, it's released, plus here H and H, here H and H, that is H2 is released, plus you get B OH here, again one OH, again OH, that is H3BO3 or boric acid, or BOH thrice. This is hydrolysis. One small thing is that addition reaction HCl, and we know this is plus and this is minus, and in this we know that here this will have N will H plus and Cl minus. In this, H plus is attacked by, okay, and this electron goes to when this is cut, this will get HCl and all, like it will just basically form and we'll just do Cl. Basically this Cl minus will go to this and this will form minus and H plus will go here. This H plus is like attracted by the lone pair here. So this is how the addition reaction looks like.